right, good afternoon, and we will, hopefully everybody's making steady progress on homework 3 and lab 2. Okay, making progress? Not started yet? Well, like I said, yeah, I know. So, yeah, but like I said, homework 3 covers a little bit of the proportion chapter and some of the mean chapter that we just finished. And those are within the scope of the midterm. That's why I was hoping that we all can do that more practice before taking the midterm and all that. And then the same for the lab as well. So lab 2 is on the mean chapter. Okay, and it's very similar to what we have done before for the proportion in lecture, you know, the different inferential questions. So that I think, and I believe will give you enough practice for doing those as well. So both are due on Wednesday, and the goal is really just to also let me be able to grade lab 2 and return for your take-home portion, as well as we should be able to release the solutions for homework 3 before you need to take the exam on Friday. Okay, so that's why the deadline is a little bit challenging, I'm sure, but nevertheless, happy to work on alternative deadlines. If you need anything, you just need to let me know as soon as you can, and then we can go from there. And I also made some responses, I think, on Monday, emails about what you should expect in the exam and all that. So just so you know, we did all of those exercises in class. So we are able to practice how to deal with Bayes rule derivation for posterior. But nevertheless, like I said, you will be able to bring a 2-sided cheat sheet prepared by yourself to the exam. You can write down whatever you want. But per question, I think asked in the email and the weekly check-in, I would just say that you should not expect to see exactly the same derivation that we did in class, okay? Because otherwise, well, what's the point of taking the or giving the exam? But the goal is for you to know how to derive posterior using the general techniques that we have covered in a relatively new setting. Okay? So if you want to review, I think what you can do is, of course, the beta binomial that we derived in class, the normal, the gamma normal that we did. I think if you're able to do it from scratch by yourself after you do the exercise and review, I think you should be all set. Okay? So nevertheless, definitely it is challenging to some degree for some of you. And you will see soon that, especially starting from this chapter, we'll focus more on the computing side. And then we're going to do some kind of computing using our own coding in R. But later on, we're going to introduce the software that will do most of the estimation of the model for us. So after this, and then the last 2 chapters of our course will mostly about application. Okay, so that's just the transition and a preview of what you should be expecting. So for today, we're going to start the Gibbs sampler and the MCMC. So MCMC stands for Markov chain Monte Carlo. That's the main estimation method for Bayesian model. And then Gibbs sampler is one MCMC algorithm. So I'm going to motivate how to deal with Gibbs sampler using our normal data example that we had done. And then we're going to see how we can do MCMC estimation using software. So the example is the same as before. We're still working with the consumer expenditure surveys. We're looking at the expenditures variable. So this part might be a little bit review, and then also like maybe repeating what we did before. So that's the data set that I posted on Moodle. It's from the consumer expenditure survey. And we're working with the total expenditure from last quarter, if you remember that variable. So we looked at its summary and standard deviation. And of course, we plotted and we realized that it's a highly right-skewed distribution, right? So we took the log and then make everything a little bit nicer to work with. And eventually, we are modeling this log version of the total expenditure from last quarter, and that's the data model. Okay? So in last chapter, we've been working with, well, what if I don't know mu, but I know sigma of this normal model, and then we introduce the conjugate normal. Okay? The other one is we introduce what if you don't know sigma, but you know mu, and then we introduce the gamma conjugate prime. Okay? So that's what we did in last chapter. So of course, we also review this normal distribution. So hopefully everybody is so familiar with it right now with all of the exercises that we have done. And with that, we also did a little bit review, if you remember, about the normal density. It has a mean, it has a standard deviation, and how it changes the shape and everything. The IID normals is also what we focused on a lot. So that's how, if you remember, equation 1 is how we're able to write out the likelihood function of mu and sigma. Okay? They all come from this assumption that we assume that the sequence of observations, they are identically and independently following a normal distribution with the same mu and sigma. So equation 1 is the, I guess, the basis of how we're able to write out the likelihood in the first place. So this is also a review from before. All right, so to motivate a more complicated situation now, so remember, we used to have only one of the parameters is unknown, either mu or sigma, the standard deviation. But now we're gonna come back to the most basic situation, that what if both of them are unknown, and how can we give prior and try to figure out posteriors for them? Okay, so if you remember, for step 1, we're having this prior distributions, and we know that if both are unknown, if you remember what we used to write, I write this L, and then as a function of mu and sigma. Okay, so later on, what we did last chapter is we assume one of them is known, so we delete that from our likelihood function. But the very basic version of it is that both of them are unknown, so we have a likelihood function of both of the two unknown parameters. Okay, notation-wise, whatever is unknown, that will go into the likelihood function, and it is a function about the unknown parameters. So what we did, I think we introduced this before, we just didn't go into the detail, is, well, if both of them are unknown, we are going to work with a joint prior distribution. Generically, we write pi, mu, and sigma. So whatever is unknown, you should include them in the way that you write out your prior distribution. And similarly, for the posterior, it's a joint posterior. So notice how we're using those terms. They're joint in the prior, in the posterior, because we're looking at the joint distribution of them. Okay, right now, we don't know what prior to give at this moment, but at the very least, we know that Bayes' rule goes this way. You have a joint prior, you have a joint likelihood, L, mu, and sigma, and then eventually Bayes' rule going to help us derive a joint posterior. Okay. So that's the setup, as we know. And what we did before, as you know, if only mean is unknown, the mu is unknown, then remember we put sigma behind the conditional sign to assume that we know it. And in the slides, I actually color code them in red, so we know that they're all known. And equation 7 is the main result from last time, okay, that we know the posterior distribution for mu is another normal if I give it a normal prior. And we actually introduced the notation of phi, which is 1 over sigma squared. So that's the precision parameter. It just like mathematically works easier if we use this as the notation. And we looked at in R, you're able to code it because all of the mu 0, sigma, phi 0, and phi and y bar, and all of the other are constants. So once you know them, you're able to actually summarize the posterior distribution of mu. So that's what we did. For one situation, the normal conjugate prior for mu, if sigma is known. The other one we did, which like I said, was much easier to derive, is when sigma is unknown, but mu is known, then we're working with a gamma conjugate prior. So we start with a gamma, and we arrive at a different gamma. The derivation we did in class, all of the terms are known because alpha, beta, they're the priors that you give. Okay, n is the sample size, and then yi is given once you get your data, and mu is something we know as well. So with the equation 10 of the results, we're able to figure out exactly what the posterior distribution of 1 over sigma is, which is phi in this case. And then we'll be able to use R gamma to sample large numbers of it and then try to do, Bayesian hypothesis test, okay, Bayesian credible interval, as well as predictions. And all of those are in lab 2 if you already started working on it, but this is the connection to what we have done already. Okay, all right. So if all sounds good, then let's go back to the case where both mu and sigma are unknown. Okay, and you might be, okay, what we're gonna do, and this is notation, like I said, we have a joint prior, for both of them, mu and sigma together, okay? And what I want to motivate us to think is that, well, if we assume one is known, the other is not known, then we actually know two conjugate priors that we can work with. Okay, so for mu, we know that normal is a conjugate prior. And for sigma, or 1 over sigma squared, we know that gamma is a conjugate prior. So let's start with the simplest case in equation 11, that, okay, I need to specify a joint prior for mu and sigma. I know that each of them, we have a conjugate result that can be really useful. So how about we assume that mu and sigma are independent from each other? So their joint distribution is the product of their marginal. Okay, so notation, as we know, if mu and sigma are independent from each other, then pi mu sigma, that's the joint density of mu and sigma, becomes the product of their marginal distribution. So just to make the notation a little bit easier to read, I do pi 1 mu and pi 2 sigma. So joint density of two independent variables is the product of the marginal of the two. So this is from probability course, hopefully from the past that you remember. Okay. And we're actually going to do something very similar to what we did before. Let's give mu the normal prior that we worked before, which is conjugate. And we have that complicated results that we know from before. And let's also give 1 over sigma the gamma prior that we worked before. Okay. So remember what we did before is that when we give mu as this normal prior, we assume that sigma is known, okay? And we know that it's a conjugate result. So we have a conjugate posterior that we work with. And then when the other one, when mu is unknown and 1 over sigma squared is unknown, we know that gamma gives the posterior as another gamma as well. So we motivate doing this. Of course, you can give other priors if you want. And mathematically, it will be much harder to work with other priors, which I will show you why we want to give this equation 12 and 13 for now. But soonish, like I said, I'm going to introduce certain software that can do the estimation for you. So at that point, you can give whatever prior you prefer. Okay? But for us, I want to show you that, well, Markov chain Monte Carlo is nothing like fancy or something. We can actually give certain priors that we can work with, and we can code it to let it run. And but then, of course, those priors need to follow certain form, like equation 12 and 13. But once we're able to work with software that can be all-purpose, what kind of estimation you want to do, what kind of models you want to work with, then you're definitely not limited to the priors that we're covering right now. Okay. All right. So let's get the fun part. So this is the results from before. Okay. And like I said, we have phi, which is 1 over sigma squared. Okay. And mu, again, is the mean itself. So what I'm claiming right now, which we're going to do a little bit of derivation exercise, which you can borrow what we have done before, is that, well, if I give two independent marginal priors, one for mu as a normal and for 1 over sigma squared as a gamma, I will arrive using Bayes' rule of two, what we call full conditional posterior distributions. Let me explain that a little bit. So remember, we used to have posterior distributions if we're working with one parameter at a time, right? So maybe refresh our memory a little bit. If we have mu as a normal, if you remember mu 0 and sigma 0, I think that's the prior that we work with. And then we have our data, even mu and phi follows a normal mu and sigma, okay, IID, okay. And then we know that the conjugate result gives us mu given y1 through yn, okay. And then it's a particular normal, let me just write mu n and sigma n, but it relates to equation 14, what we did the derivation before, okay. So what I'm trying to show you over here is that, well, if you only have one parameter as unknown, let me use a different color. Oops. Yeah, if I have my one parameter as unknown, then I work with the prior for it. I have a likelihood function from the joint density, and then eventually I have a posterior distribution for mu. Okay. And similarly, if I work with 1 over phi earlier with the gamma, then that's what we have as well. right now, if you remember, both mu and phi are unknown. So we have the joint prior of something. Okay, so remember we have one for normal and then one for a gamma. Okay, so let me just use the notation a little bit abusive notation over here, but we are using the joint prior as the product, if you remember. So I'm just writing it over here. And then eventually, of course, we want the joint posterior if we can. But the joint posterior might not be something easy to recognize if we're trying to do the derivation. Okay, so what I'm proposing now is instead of trying to get the posterior, joint posterior, we're going to come up with the term, which we're going to work with, is called the full conditional posterior distribution. So what I mean by that, the full conditional posterior distribution for mu, because it's conditioning on everything else. Okay, so it's conditioning on all of the data, and phi, which I know is unknown, but suppose it is known, it's going to be after the conditional sign. Okay. Similarly, for 1 over sigma squared, which is phi, its full conditional posterior distribution going to be conditioning on all of the data, and then whatever else is in the model, which is the other parameter. Okay. So if I try to define full conditional posterior distribution for any parameter in the Bayesian model, you can just write, say for mu, it's going to be deconditioning all of the data, as well as every other parameter in the model. In our case, it's only phi, so you only need to write down phi. Okay? And then for phi, it's going to be all of the data, and then all of the other parameters in the model, which will be mu. So sometimes people write, and I think I introduced the notation last time as well, just to save space, you can write a short or maybe a little bit longer hyphen, just to indicate that I'm conditioning on everything else in the model, which will be the data, as well as any other parameters. Okay, okay, all right. So now, let me ask you to give it a try. Okay, so clearly, we're trying to come up with this distribution. Okay, and we're also trying to come up with this distribution. And we have a joint prior, which is a product of two marginal prior, okay? And we have a joint likelihood, as we know, is gonna be how we can write out the joint density given mu and sigma at the same time. Okay? So as we know, by Bayes' rule, the posterior distribution of mu and sigma gonna be proportional. Sorry. Given all of the data, they're going to be proportional to the prior and the likelihood. Okay, so we can write out all of the complicated terms together into the joint. So we have normal times the gamma, and then a joint normal over here. And what I'm proposing now, which is what we're going to do a little bit exercise over here, is that, well, from this joint posterior, I'm trying to find out everything about mu only and try to recognize what the distribution it is. And then I'm going to find everything about phi only and then trying to figure out what the distribution is. Okay, so let me say that again. Equation 14 and 15 is a goal that we're trying to work towards to. So I'm claiming from the joint posterior distribution, if I figure out all of the terms together, which will give you the chance to do that in class, if then I try to find out anything about mu, trying to find its full conditional posterior distribution, I'm claiming that you're going to get to this normal result. And if I'm now looking at everything about phi, so meaning that I'm conditioning on the data as well as the other parameter, I'm claiming that you will get to equation 15. So a lot of the exercises that we did before from last chapter will be super useful, because one thing, even without doing the derivation, if I look at equation 14 and 15, they look exactly the same as what we did before. Okay, but the concept is slightly different now. So what I'm trying to emphasize at this point is that here we're assuming that both mu and sigma are unknown. So we have a joint prior, we have a joint likelihood, and then we should arrive at joint posterior. So, but when you work with it, well, you always have the prior multiplied with the likelihood. And we know that in our posterior derivation, If I'm trying to find the posterior about mu, I only need to care about every terms about mu. If I'm looking at the posterior distribution about phi, I only need to look at every term about phi. So in our full conditional posterior distribution derivation, the same rule apply. Okay, so with that in mind, I will pause and let you work out some of the details. Like I said, equation 14 will be harder to derive, just like what we have seen in the previous chapter. 15 is slightly more, slightly less challenging, I think. But nevertheless, I think working through the general procedure one more time, well, definitely helps us understanding the new chapter, but it could be a really useful review for the previous chapter, which can be useful again for preparing for the midterm. Okay, so what I'm asking you to do right now is try to write out the posterior, joint posterior, following Bayes' rule. And I write it out for you over here, the general rule. And then from the joint, try to find out the distribution of mu given everything, which should be equation 14, and try to find out phi given everything, which should be equation 15. Yes.
So the procedure is basically the same as the other derivations that we did, and it's just that technically they're joint priors, but when we're deriving the full conditional posteriors, we kind of treat them as if they're not joint.
Oh, good question. Okay, yeah. They are joint. Okay, so no matter what, okay, so yeah, we'll come back to this slide. So Noah's question, let's come back here. So we should give a joint prior no matter what, okay? But what I'm proposing is let's start simple. Let's just give them independent priors. So the joint distribution, if two things are independent from each other, mu and sigma, then the joint distribution of mu and sigma, which is the prior, should be the product of the marginal of their own priors. So you can give other joint prior that mu and sigma might have some relationship going on. I don't know. We don't deal with it, and at least not now. But if we start simple with the equation 11 and specifically giving mu the normal prior that we did before, okay, and giving phi the gamma prior that we did before, then at the end of the day, we are trying to derive what we call the full conditional posterior distribution, which is, if you look at the joint posterior, I'm only looking at anything about mu, and I'm only looking at anything about phi. Okay, so at the end of the day, so that's why earlier I was trying to write, you should be writing out the joint posterior following the joint prior multiplies with the joint likelihood. And of course, it depends on what the prior is, what the likelihood is. You have to throw in all of the terms. But if I'm only looking at full conditional posterior for mu, then I only need to care about what mu follows. I can assume at that point that phi is known. Okay. And similarly, I do that for phi. Okay. So give it a try. It will be something very similar as what we did, just like what Noah was pointing out, because we are giving a independent prior. So once I put everything in, even though when I'm trying to derive the full conditional posterior for mu, I have new terms about sigma from its prior, but it's known, so I don't even need to worry about it. And that's why eventually equation 14 and 15, they look exactly the same as what we did before, if we're only looking at one parameter at a time. Okay, so I'm going to pause now because I think doing it might solve some of the confusion, but of course we're going to look at it together in a second as well. And let me pause here. Yeah, in your derivation, you probably need to go back to equation, so which is slide 14, the priors. Okay, so the priors are the normal and the gamma. And so you need to know equation 12 and 13, and you can probably look at your previous notes from last chapter. And then eventually you should arrive at equation 14 and 15. Hopefully you will get there soon. All right, so to help us to make sure that we know the general process, okay, I'm just going to do the first few steps and then we can recognize things hopefully pretty quickly, because like I said in the previous chapter, we have done those very complicated derivations already, and what we're doing here right now is not very different from it. So whatever you have graphs before can be directly translate back over here, okay? But for the both mu and sigma unknown, we just wanted to make sure that we have set up the stage correct, okay? So the prior, as we know, is the product of the two marginal priors, okay? So if we write using the notation that I offered earlier, so we're gonna have our pi of mu and sigma is the product of pi 1 mu multiplies with pi 2 sigma, and we know that for mu we give a normal, right? And for sigma, or 1 over sigma squared, we give it a gamma. So what do we have? We're gonna have 1 over 2 pi, and I think, what did we use? Sigma 0 squared, okay? And then in the exponent, because it's the prior about mu, so what we have negative, for some reason it's not working. Give me a second. Yeah, and not sure my, okay. 2 sigma 0 squared over here, and it's going to be mu minus mu 0 squared, right? That's the normal prior. Okay, yeah. For 1 over sigma squared, if you remember, we give a gamma, alpha, and beta. Okay, so what that is I think is, what is it? Beta to the power of alpha, and then gamma alpha, and then we have 1 over sigma squared to the power of alpha minus 1, and then in the exponent we have negative beta times 1 over sigma squared, right? That's just the regular normal density and the regular gamma density to help us get everything started. Okay, yeah, I'm keeping the constants for now, but as you can see later, once we start to do the base rule derivation, those constants can go away if we don't need to worry about it. But for now, we can keep everything in. So later we can cancel the terms at the same time instead of making mistakes. Okay. All right, the likelihood, which I hope everybody is super familiar now, we know is the joint of y1 to yn given the two parameters. Not sure okay, yeah, the pen is not working too well. Okay, sorry about the space, but there shouldn't be a space over there. And we know it's the joint. Oops. It's the joint, which means it's the product. Okay, and for each of them is a normal density. So we have what? 1 over 2 pi sigma squared. Okay. And then in the exponent, we have negative 2 sigma squared in the denominator, and yi minus mu, take the square, right? And of course, this is the whole thing taking the product because each of it is just a normal density. And we can do a little bit more simplification, just like what we did before. We are producting all of those terms. So for the first one, we're gonna get 2 pi sigma squared, the whole thing to the power of n. And then in the exponent, we have the sum in the numerator because the summation is about yi. Okay, okay, yeah. So this is what we did in chapter. Well, what's different now is right now the joint. So we have a joint prior, and it's the product of two marginal priors. So we just really putting it, multiplying together with each other. So the first one and the second one. The likelihood actually is exactly the same as before. Okay? So no matter which ones you're assuming to be known or unknown, but if both are unknown over here, you're gonna have the joint likelihood as is. So like I said, the rest shouldn't be too bad. So we're gonna have the product of the prior and the likelihood should give us proportional to the joint posterior. Right, that's the base rule. So if I need to know the joint posterior, it's gonna be, according to base rule, proportional to the joint prior times the joint likelihood, which I have done already above. Okay, so I have my joint prior and I have my joint likelihood. All right, so the first test, right, is about mu. So remember, the first task is trying to find out the posterior distribution or the full conditional posterior distribution of mu given y1 through yn, it should be n, and sigma. So in order to find this full conditional posterior distribution, I just need to find out of the products of the prior and the likelihood. I just need to keep everything about mu because everything not about mu is a constant. I don't even need to worry about it. Okay. So what should I keep? Let me use a different color over here. From the prior, where is mu? Mu is here. Okay, so we definitely need this whole term, right? And then from the likelihood, we only need this term, right? Yeah. And when you do that, we actually just go back to the previous chapter. Because the previous chapter, we didn't have sigma as unknown, so we don't even need to deal with sigma in the first place, right? If I only need to find anything about mu, what do I need? I just need to collect all of the terms from the product. So by the way, because of the space, it's harder for me to write out the product in one more line and then showing the rest of the work. But this product is the product of this and this. Okay. So right now I'm just trying to go back to the product to, let's just say term 1, term 2, and term 3. And just say 1, 2, and 3. It's the product of all of this together as the joint posterior. Okay. And from the joint posterior to the full conditional posterior for mu, I just need to go back to 1, 2, and 3, and 1, 2, and 3, all of the terms, and only look at the terms about mu. And when I do that, let me just write that out so we get one example going. Proportional to what? exp from the prior, I have 2 sigma 0 square, mu minus mu square. And then I also have in the exponent -2. This is from the joint likelihood. I have the sum of yi minus mu square. And if you check what we did before from previous chapter, that's exactly what we left with when we were trying to derive the posterior. So that's why we get exactly the same result as before in, I guess, equation 14. Okay. So task 2 is trying to find out, let me use 1 over sigma squared so it's a little bit easier to deal with. And mu, okay. So let me use a different color. So now my goal is to find any term about 1 over sigma squared. So if I go back to the prior, I have things about 1 over sigma squared over here, right? What I circled in green just now. So that's all the terms about sigma squared. Everything else is not about sigma squared from the prior. And then if I go to the L mu sigma, that's the joint likelihood, I actually have the whole term that I need because all of them is about sigma squared somehow. Okay. So if I do that, you will see we once again went back to previous chapter if we're trying just to derive the posterior for sigma square, 1 over sigma squared. So we have from the prior, and then from the likelihood, I think we did this 1 over sigma square, if you remember, to the power of n minus 2, n over 2, sorry. And then whatever we have over here is in the exponent. Okay. And this, once again, is exactly what we did from the previous chapter. If we only assume sigma is unknown and mu is known, then we eventually, from this last line, we recognize a gamma posterior. Whereas over here, we call it full conditional posterior distribution, simply because what we're working on right now is both of them are unknown, but we give independent priors. So the other parameter, if we're trying to figure out the full conditional posterior distribution, so for mu, we know that it's conditioning on the data as well as the other parameter. For 1 over sigma squared, it's conditioning on the data as well as the other parameter. So derivation wise, it goes back to what we did before. Okay. Okay. So the goal, or I should say the most important lesson that we're learning here right now is that we're giving joint prior. And because of that, we have a joint likelihood. In this case, we have two parameters, mu and sigma, both unknown. So we work in this way. Maybe in a different exercise, which I think I prepare something for Friday for more practice as well. When you have more parameters to work with, if all of them are having their own prior, you just need to put everything in. Okay. So for example, I will keep this over here, but I will just cap little space. Okay, let's just say in a particular model, I have three parameters, theta 1, theta 2, and theta 3. And let's just do 4, theta 4. Okay, so I will probably tell you what the priors are for all of them. Okay, but eventually what you have is a joint prior in whatever format for all of them at the same time. Okay, and then I will also give you the data model. Once you get there, you will have a joint likelihood for all of them. Okay. And then from there, you should be able to get the joint posterior. So I will use this notation to represent that it's conditioning on all of the data over there. It will be proportional to the prior multiplies with the likelihood. Okay. So this is just the general process. No matter how many parameters you have, if all of them are unknown, then one way or another, you're going to have a joint prior for them. You're going to have a joint likelihood for all of them. And then eventually, you're going to have a joint posterior for all of them. For us, derivation could be way more complicated, right? So with that, I'm just going to erase part of this so I can have some space to show you what we mean by that. So if we now have the joint posterior, it might be really challenging to derive the joint posterior, to recognize it as something. So it's going to be hard to, summarize the posterior. So what we do is we introduce this full conditional posterior distribution. So generically from here, if I want to find the the full conditional posterior distribution for theta 1, all I need to do is from the product of its prior and their likelihood, I find every terms about theta 1 and try to recognize what it is. Similarly, I do that for theta 2. I do that for theta 3. And I do that for theta 4. It's going to be something, will be very problem specific. Okay. But you can see that for us, when we're working with the normal model, we only have two parameters. So we have mu and sigma, and you have the joint prior, the joint likelihood. From that, you get the joint posterior. And from that, you get the full conditional of mu, given everything, including sigma. And you get that for phi, or 1 over sigma squared, given everything, including mu. Okay. Okay, so I'm trying to write out something like generic at this point, but I would say right now, the most important thing, I guess, is to recognize there is this general procedure, but specifically for what we did. So let me come back to the slides. Okay. Specifically, what we did is that we have this joint prior, which is the product of the two marginal, because we assume they're independent from each other. We give a prior for mu, we give another prior for sigma, or 1 over sigma squared. And through derivation, we will be able to recognize the full conditional posterior distributions in equation 14 and 15. We see that the results resemble very much of what we have done in the previous chapter, but the concept is now different, because previously we only have one parameter at a time, and we call them posterior distribution, but right now we have both parameters as unknown, so we are deriving what we call full conditional posterior distributions. For mu, it's conditioning on all of the data and every other parameter. For phi, is conditioning on the data and every other parameter. The results look very similar, and it's not surprising because we gave independent priors, right? Like I said, with independent priors, when you multiply the prior together, if I'm just working on the full conditional posterior distribution for mu, I don't need to worry about anything about sigma. Okay, if I'm only deriving the full conditional posterior distribution for sigma, I don't need to worry about anything about mu. So even if there are extra terms in the prior, it doesn't really matter. All right, so If all of this makes sense, hopefully, I want to show you why we want to do the full conditional posterior distribution, because this can help us a lot with the model estimation process. So the Gibbs sampler or a Gibbs sampler is based on the availability of full conditional posterior distribution. So at the top, I repeat what we had from the previous slide. Okay. So what we're going to do eventually is that we're going to iteratively sample mu and phi and mu and phi and mu and phi and mu and phi. Okay. And the way that we are sampling it is from this full conditional posterior distribution. So let's just say in my model estimation process, let's just say I have an initial value for mu and I have an initial value for phi. I use parentheses 0 in the superscript to indicate that they're the initial values. Okay. You're going to see that we're going to iteratively sample mu and phi, and then we're going to indicate which sample it is. So, but at the starting point is 0 at the initial value. So I'm just going to label them as mu 0 in the superscript and phi 0 in the superscript. The way that we're going to simulate our posterior distribution, again, this is multi-color simulation, you can think about it, but specifically including Markov chain over here, is that we're going to do this for a large number of times. As you can see, I always use capital S to indicate how many iterations we're doing. So for each iteration, we're going to generate the following sequence from the full conditional posterior distribution from the two that we derived together. Okay. So for example, at one iteration little s, for mu, what I need to do, I just sample from this normal distribution, okay, where I have all of the data, okay, and then of course I need to use the previous iteration of phi so that I can sample a mu. Okay. And then once I have my mu s, so I finish this step first. I have at my iteration s, I have a draw for mu. I do that for phi coming from the second full conditional posterior distribution. So it's a gamma. So I'm going to do R gamma literally in R. When you're sampling it, you're doing your R gamma from the previous draw that I just did for mu, and then all of the data that I have. Okay. And then for iteration S, I have a set of mu and phi to be ready for the next step. So the iterative process, as you can see, is actually a basis of why we call it as Markov chain. So some of you might know about the term before. Basically, you can think about, if you look at mu s, it depends on phi s minus 1 from the previous step. And then for phi s is coming from the current step of mu. And if you think about it, well, mu s, I should say phi s, even though not directly depend on phi s minus 1, but because phi s minus 1 indicates how mu s should be, and mu s is part of how phi s is generated. So if you're only looking at phi, they're related to each other. Okay. So the previous step, even though not directly impacting the current step, but it's indirectly with one more step in between from the other parameters. Yes, Noah? So
does this always converge?
Great question. Yes. So we're going to look at, after we cover some of the other computing and everything as well, the question, what Noah was saying is, yes, we can get a bunch of draws, of course, of mu and phi. So there, I guess, one general question will be that, do we have all of the draws, let's just say 1,000 or 10,000, however many that we have? Can we be sure that they're going to converge to the true posterior? So this is actually a question we're going to try to discuss later. What you're going to find is that there's no real way to make sure that they definitely converge, but there are ways to check that they have not converged. So you're going to see what we introduce as MCMC diagnostics, meaning that, well, we have certain measure we're going to introduce. And if some of the measures, as you can see visually or computationally, numerically, I should say, if they show some problems, then you probably need to run the chain a bit longer, or some other techniques that we're going to introduce. Yes, Kara.
Sorry, for clarification.
Yeah.
So it's taking different values and running them as number of times.
Yeah. So right. So okay. So we set at this iteration both parameters. We have mu s and phi s at this particular iteration, and we're just saying that the joint of them, because it's a joint distribution over here, may be viewed and not necessarily, so that's what we mean by the diagnostics that we're going to do, going to be a dependent sample from the joint distribution of mu and phi eventually. So in practice, what we get, and you will see in the codes that I'm going to show in a second as well. And we got a question which I'm going to try to address in a second as well. You'll see that in practice, what we're going to get is we're going to get a sequence of draws for mu, okay, and we're going to sequence of draws for phi. Okay? So once we have done all of the iterative process, and we're going to check if they indeed converge to the true posterior. And indeed converge actually is just to check that they have not have any issues of non-convergence. So that's what we're going to do, called diagnostics. And then eventually we can summarize the posterior draws of this mu. If I want to know a 95% credible interval, right? I can summarize using the quantile function that we have done before. And you can do that for phi as well. So I think in practice, you do get a sequence of draws from this Gibbs sampler. And eventually, once you have, once you're able to check that the diagnostics have passed, then you're able to summarize the posterior. So the question is, it seems like mu0 is never used, only phi0 is used in the sampling. Is this true? All right, good question. So as you can see over here, I'm just showing a very generic result over here, like mu, sigma, mu and phi. And I'm saying that, well, let's start with mu0 and phi0, okay? And you can start with whatever value you want, okay? And then you're going to do this iterative process. Toga's question is, based on whatever the procedure that I presented over here, it seems that mu0 is never used, only phi0 is used. So as you can see, in this particular way that I presented, let me actually clear over here. In this particular way that I presented, you can see that, well, we need a phi0 to get a mu1, right? And then from a mu1, I can get a phi1, right? And then I can use my phi1 to get mu2. From my mu2, I can get my phi2 and et cetera, iteratively this way, okay? So yes, generically, you can write that for two parameters. I will have initial values for both of them, but it's not necessary that both of them might be used. So for example, if I reverse this two order, okay, that I start with mu0 first to get my phi1, and then from my phi1, I get my mu1. And when that happens, you probably will never use phi0 in that case. Okay? So because the iterative process, so I guess to Toga's question, yes, true. In the particular way that I'm presenting over here, you would not use mu0. So specifically, I guess for this case, we have two parameters. So you can give them both initial values, but not all of them going to be used. And generically, I think if you have more than, well, you use Gibbs sampler when you have more than one parameter. So really, because of the iterative process, it's always univariate. So essentially, you can give them all initial values, but most likely only one of them is needed for getting things started. Okay. Yeah, so there are multiple ways to do it, but you will see that, well, if a Gibbs sampler hopefully successfully converged, then the initial value shouldn't matter too much. Okay, so that's why, and whether you start with mu or whether you start with phi should not matter too much either. So in that case, you can start with whichever, and you can probably code it multiple times as you wish, and then see if they all converge roughly to the same parameter space. So with that in mind, I do want to show you the code a little bit. And of course, the code is posted on Moodle, so you can look into a little bit more later. But we coded here as a function. We call it the Gibbs sampler for the normal model. Okay? And we need the input, that's the initial values as well as the data and everything. We need the number of iterations that we want. And then because this is a random process, you may want to pass a seed in your function so you can get reproducible results. Okay? So what you can see over here, we set seed in the function. We compute the y bar because y bar is the important value that we need to use in our update. We also need the number of observations. And here specifically, I'm creating a matrix to store my parameter values. I get a matrix of zeros to start with. I have S number of rows and 2 number of columns. So essentially, I start an empty matrix. And the first one, I'm gonna store everything about mu. And the other one, I think I called it phi. No, so I'm gonna store everything about phi. And then this is about each iteration. Okay, so remember, because we're gonna do this in an iterative process, eventually we want all of the draws to be used for our posterior inference. So that's what we're gonna do. Okay. And like I said, the input should also have something about the initial value. So in our demonstration, we just need the initial value for phi. So I'm gonna start phi over here. And then I have a huge loop. And this loop is really looping through the Gibbs sampler that we showed earlier. Okay. So we first of all get the new mu. And then from equation 14, and we get sigma 1 or new sigma from I think, yeah, from, oh, let's see. Yeah, okay, let me take that back. I think here, mu1, sigma 1 are still representing the parameters for those normal and gamma draw. But regardless, we get a mu, we get a sigma, so we're able to do a random draw of normal using mu1 and sigma 1. So we're able to get that equation 14 work. And then we prepared for equation 15 to get a R gamma draw from. So the calculation, again, may look a little bit complicated at the beginning, but since we write it up into a function, if you're dealing with exactly the same problem, like you give a gamma prior for phi, and then you give a normal prior for mu, and you have all of your data, whatever, you can use exactly the same function for your Gibbs sampler. Okay. And then eventually, as you can see, because I want to store all of the parameter draws from all of these iterations, I'm just gonna store my S iteration of S row of my big matrix to be the vector of mu and phi. So I can store them one by one in this loop. Okay, okay, okay. All right, so of course we have some results, and oh, let me see. So this is the function that you can write. And then if I want to start running it, I just need to give the input. So I have all of the y that I need, okay? My normal prior, and my gamma prior, and my phi initial value, let's just say it's 1. And then I can run this function. From the input, I'm running it for 10,000 times. I'm using seed 1, 2, 3. So this whole output should give us the big matrix of the first column of all of the mu's and the second column of all of the phis. Okay, so with that, we can extract the posterior draws, and then we should be able to summarize. So I want to show you, well, we can do a little density plot. Sorry about the size. I just need to squeeze in everything on one slide. So it's a little bit small, and I think this is supposed to be about mu. Okay. And then I can do a posterior 95% credible interval using quantile, because I already have all of the draws of mu. Okay. So that's for mu. And you can do that for phi as well. Okay. And yeah, so of course they have different range and everything, even though overall they might look similar. But that's the posterior of phi, and this is the posterior of mu. You can do all kinds of summary as you wish. So with that in mind, I do want you to think through. If you have your computer, great. If not, don't worry. I still think it's useful. I'm gonna talk about the 2 exercises and go back to the slide where we have the code and give you the chance to talk to your neighbors to see which part you're going to change in order to make it work. Okay. So I think, yeah, let's just focus on exercise 1, because I think 2 might not be as useful. So 1 is whatever the sampler I show you, which we're going to go back in a second, try to update the sampler to initiate it with mu initial value instead of phi initial value. Okay. So keep that in mind. Let me come back to this slide where we have the code and take a moment to think about where you're going to change to make that happen. So the question is, use mu initial instead of what we have using the phi initial. Okay. So the sample, Gibbs sampler over here on this slide. So by the way, later putting people in the breakout room, make sure that you're looking at slide 17 of the lecture slides. So in this particular example, we initialize, right, the whole process by mu 0, by phi 0. Okay. So my question is, how can I change the code? Which lines I have to change and blah, 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 in order to start a new Gibbs sampler that I start with mu0 instead of phi0. So take a moment. I'm going to pause here and chat with your neighbors. I will also put people, remote students, to a breakout room so you can chat about it as well. And then we're going to talk about it together. If you have your computer and want to play with it, go for it. At least in class, we should talk about what we should be doing in order to make it happen. And after class, this could be a really good exercise as well. All right, so maybe I can just ask whoever wants to share what you have found. Yeah, we can talk about it verbally, but like I said, exercise 1 will be super useful after class as well to help you get a solid understanding of the code, as well as, well, the second half of that question is, can you compare the results to whatever we can get over here and see how close they are? Because if you remember, I was saying, if eventually the Gibbs sample are going to converge to the two posterior, then wherever you start shouldn't matter too much. Okay. All right. So the question is, well, if I want to start with initial value, mu0 instead of phi0, what should I do? So there are many lines, I guess, in this function. At what place should be the first change that I make? Anyone? Yeah, Rachel. Yeah, exactly. So instead of this, well, I'm just writing the code, but hopefully it makes sense. So we're gonna do, okay, it's probably my first time writing down $sign, trying to write the code. Okay, so in the initial input, I should say, we can save a value for mu as well. So if that's what we do, okay. Is that all I need to do, or I need to do something else as well? For the entire code, I mean, not just that line. If I change this and run it, am I ready to run it, or I need to do something else as well?
I think you need to start.
Go ahead. Yeah.
I think you need to start somewhere else. I think you want to start from sigma.
Yeah, exactly. Okay. So basically, we actually need to swap this block with, let me just use a different color, with this block. So I should have my blue box first, because we start with mu. Okay? So you need to get a first phi, because otherwise the whole loop wouldn't run. Okay? So I should get my blue box first, and then get my red box next. There might be some little things we need to change. Oh, I guess it's fine, because here its name is mu and its name is phi. So that's why it's useful. So when you start actually coding it, I hope you will find the function useful, especially, I mean, not only about the general flow, but also about how we name those parameters. Okay? Because as you can see, the way that we write it is, well, whatever in the loop, phi is called phi and mu is called mu. We don't do like a phi1 or phi2, whatever, you know, because that can make it very easy to swap the different blocks if we start with a new initial value. Okay, so the general things that we have to change is this line, which we did, and then the swap of this two. And so like I said, after class, if you want, try to write a new function by swapping the two blocks as well as changing that line, and then see if you get something very similar. Hopefully you do, to the two posterior summary that we have done over here. So this is the one that we did in class for mu, and this is for phi. And if you swap it out and do the reverse order, you should get something similar as well, meaning that it doesn't matter whether I start with mu or whether I start with phi. And if you want, you can even try to start at different values of the initial values and see if eventually you get something similar. Okay. So we will have a chunk of lecture to talk about the diagnostics of the markup, I mean, the sampler itself. But for the very basic intuition, I hope you agree that, well, if indeed the Gibbs sampler has converged to the two posterior, then it doesn't matter if I start with mu or phi, And it doesn't really matter if I start with mu at 10 or if I start with mu at 5. I don't know, I'm just making up those numbers. Because eventually, if the model is stable, if the estimation has done properly, it doesn't matter which parameter I start with, and it doesn't matter where I really started. Because eventually it should come to the same area of the values that I'm supposed to get. Okay, so we're going to look at that later as part of this, I think this chapter about MCMC diagnostics. And I also just want to talk quickly and then we can end today probably, even though we might have a few more minutes left. So you can extend this to more than 2 parameters. So earlier I was giving you the generic notation theta 1, 2, 3, 4 for the derivation purpose, okay? But after the derivation is done, we should also think about it arithmetically as well. So let's just say we have generic M, okay? M parameters in total. I'm using M1 through theta 1 through theta M. And we are able to actually get each of the full conditional. So we get theta 1 given everything else, theta 2 given everything else, up to theta M given everything else, okay? So if we try to do the Gibbs sampler by coding it, we're going to start it at the initial value. So again, you can see that we can provide a sequence of all of them or just a subset of them, okay? Depending on how many you want to do. So at the S+1 iteration, just see how we're doing all of this. If we have M parameters, we actually need to know all of the M-1 to get the first draw working. Okay, so if I look at this one, for theta 1 at the S+1 iteration, I know I'm drawing it from its full conditional distribution, and it's conditioning on theta 2 at S, theta 3 at S, theta 4 up to theta M at S. Okay. And similarly for theta 2, theta 3 up to theta M. Okay. So I have a quick question, even though I didn't write down, I guess, in the slides is, how many initial values I really need to even just get the Gibbs sampler to work or to get started? So given what we just talked about, I know earlier for mu and phi, right? We only need one of them so we can get the Gibbs sampler working. Now we have M parameters. How many of them do I need to actually be available in order to get this Gibbs sampler working? So let me pause here, give you 1 minute to discuss, and then we come back, wrap it up, and then end for today. All right, how many do we need? Can we go with only one? No, right? So let's just say if I only have one, let's just say theta 1, 0. Well, it depends on the value of M, of course, but let's just say if M is 10, then we actually need 9 of them to even get the Gibbs sampler start. Okay, so for example, you can think about instead of like theta 1 S plus 1, just try to do like theta 1, 1. Okay, if we have it, like even just to get it started, as you can see, we need theta 2 as 0, theta 3 as 0, up to theta M as 0. Okay? So yes, you can, of course, just like how we wrote the function earlier, you can put all of them in your initial value, the input that you want. But essentially, depending on which parameter you start, if I start with theta 1, then in order to get theta 1, 1, I need to have theta 2, 0, theta up to theta M 0. But if you start with, I don't know, theta 3, just for fun, then you need theta 1, 0, theta 2, 0, and then theta 4, 0, up to theta M 0. Okay, so I guess the generic result will be that if I have M parameters, I need M-1 initial values, each for one of the other parameters to get the Gibbs sample working. Okay, all right, sounds good. So I think we're gonna end here. And when we come back, we're gonna talk about, like I said, the software that we're gonna introduce, some of the MCMC diagnostics, and do another derivation exercise of a different type of model.